Well, hello, welcome again to Math 315. This is the second video for Chapter 8 on power series and Taylor series. And we've been looking at power series and how we can use the ratio test to find the interval of convergence. That is, the interval on which the particular power series converges. So as the next, I did one example of that. Here's a second example, slightly more difficult one, but perfectly reasonable. So we're going to find the open interval, and we're only ever going to find open intervals in this course. I'm not going to worry too much about the endpoints. Find the open interval of convergence for this particular power series. Again, be very careful. We've got two variables, x, and we've got k here. So the approach to this is, again, we're going to use the ratio test all the time, and so here is the worked solution to this. So again, we're going to look at the ratio of successive terms, ak plus 1 over ak, and we're looking at the absolute value of that because of the x, the presence of the x there. So we increase the power by 1, we get, so we're looking at ak plus 1, we take this, replace k with k plus 1 in both places, and we're going to divide by a sub k, and that means we're going to invert and multiply. So we turn this upside down and multiply rather than have double-decker fractions, just as we did when we were doing the ratio test. So we now got to simplify this complicated looking bit here. Do the x's first this time. So I've got an x minus 3 to the k plus 1. I've got an x minus 3 to the k. So I can cancel most of those out, and I'm just left with one of the x minus 3's. And that's the bit that could be positive or negative, so I'll put the absolute value sign around that. Now what's left is 3 to the k plus 2 over 3 to the k plus 1 plus 2. Now we want to get the limit of this as k becomes very large. And what we do is, as usual, we're going to divide by, this time we're going to divide everything through by 3 to the k. So that'll give me 1 here, plus 2 over 3 to the k. Now I divide the bottom by 3 to the k. 3 to the k plus 1 divided by 3 to the k is just 3. And I'm going to get 2 divided by 3 to the power k. Now as k now goes to infinity, so as k goes to infinity, remember the x is the variable, we keep that finite, we take a limit now as k goes to infinity. 3 to the k is getting very big, so 2 over that's getting very small, that's going to 0. Same here, this is going to 0, all that survives is 1/3. So as I let k go to infinity, I get 1/3 x absolute value x minus 1. And now I want this to be less than 1, because the ratio test says if the limit of this ratio is less than 1, then we have convergence. So I'm going to take a limit as k goes to infinity, and I'm going to force that less than 1 for convergence. These words are important. Without that, this is not true. This is not less than 1. Why should it be? It is less than 1 if we want convergence. So it's important to always write in the English as to make sense of the mathematics. Now again, I'm going to multiply the 3 up to the other side, and so I get an absolute value equation. We looked at these right back in the very first chapter. And I can unpack this now as x minus 3 is less than 3, bigger than minus 3. And if I add 3 to both sides, I'll get x's between 0 and 6. So this time we have an open interval convergence is the interval 0 to 6. So I could draw, we don't have to do this, but I like to draw little pictures. So it's the interval 0 to 6. And the radius of convergence then, we weren't asked that, but I'll put it in anyway. So the radius of convergence is going to be half the length of this interval. That's going to be 3. So that means, in practical terms, what it means is I can take any x value inside this open interval of convergence, and I can plug it back up into the original series in place of x, and this series will converge to something. Another way of thinking about that is that if I think of this as a function, then the domain of this function is x lying between 0 and 6. And again, if you replace the infinity, say, with 100, you can get your computer to plot this, draw a picture of this function. It'll sum the series up to 100 at least numerically, and you can get it to plot this. And what you'll see is you'll see a function that's only defined between 0 and 6. It may or may not converge at the endpoints. In fact, I can see that it doesn't converge at 6. There'll be an asymptote at 6, I think. And at 0, it will it won't converge there either, I don't think. So yeah, it won't converge there either. So in fact, you'll get asymptotes at these 2 points. If you've got one of these graphing calculators or computers, you might like to try that. Just put in the sum, but just go from, don't make it infinity, make it say 100, and get it to plot this thing. So these series had regions of convergence, had open intervals of convergence that were just open intervals. Sometimes we get series that converge for all x, and we're going to see one of these here. This is the sum x to the n on n factorial. We're going to prove that this series converges for all real x. That is, it converges on the whole of the real line, in which case we say that the radius of convergence is infinite, because it's converging on the whole of the real line. So the procedure is exactly the same as we've been doing, so I'll just go through that here. Now remember that 0 factorial is defined to be 1. So if you're worried about putting n as 0, it's 0 factorial. 0 factorial is defined to be 1, so there's no problem there with that. So we do our usual thing, we hit it with the ratio test. So we look at an plus 1 over an. So I replace n with n plus 1 and then invert and multiply. Now once again, do the x's first, so you get x to the n plus 1 divided by x to the n. I'm just going to get one single x, and I've got n on n plus 1 factorial. And as we've done before, once we've got things like n factorial, n plus 1 factorial, I peel off the n plus 1. So I write n plus 1 factorial as n plus 1 times all the numbers below there, that's n factorial. These then can cancel out, and so I just get the absolute value of x over n plus 1. Now we're fixing x and we're letting n go to infinity. So as n gets very big, this is some finite number over something which is becoming very big, and this is going to 0 as n goes to infinity. It automatically goes to 0. So the limit of the ratio is always less than 1. This 0 is less than 1. Doesn't matter what the x is. As n goes to infinity, for any finite x, this is going to go to 0. And so it means the series converges for all real x. And in fact, we'll see this series a little bit later on when we look at Taylor series. And believe it or not, this is the first few terms of this series are built into your calculator. This is in fact how your calculator works out. If you ask it for e cubed or e to the 5th or e to the 0.1, it actually uses this series to work out the answer, as we'll see a bit later. Well, what can we do with these series? We can do a fair bit of manipulation with these series, and that's the next little bit we're going to talk about. And we can, in fact, these power series, as we'll see, are very robust. You can kick them around, you can do lots and lots of different things with them, and nothing ever goes wrong. This is not always true for other sorts of series. There are other non-power series, infinite series, certain trigonometric series and so on, which terrible things can happen if you're not very careful. We're not going to study those in this course, but power series are beautiful. They're really very, very nice, and they're very well behaved, and you can do whatever you like with them, basically. So given two power series in powers of x minus a, That is, it's got centre A, so they look like, the first one looks like this, for example. It's the series is A sub k, and it's got centre some number A. And here's the second series, B sub k, it's also got centre A, in which both converge for x in some common interval of convergence. So we're going to suppose that there's some interval of convergence in which both of these converge. Then you can do what you like. You can add, subtract, or multiply these two series, these infinite series after all, and the resulting series will also converge in that interval. You can add, subtract, or multiply two infinite series as long as you stay in the common interval of convergence, and nothing will go wrong. And I've just done a little example here, a couple of examples here of adding and one of multiplying. The multiplying, of course, is more difficult. So we take this series. I'll do the solution over here. It's probably best to see it here. So I'm going to take this series, 1 plus x squared. This is the one we started with. This is this geometric series. And we know this converges to 1 over 1 minus x. It's a geometric series. First term is 1, common ratio x, so it's a over 1 minus r. And we know this is valid between x's minus 1 to 1. Well, we can play with this. I'm going to replace the x here with minus x. And if x is between minus 1 and 1, then minus x is also between minus 1 and 1. They're just flipping around the origin. If I do that in the series, so I replace this x with minus x. Now when I square minus x, minus squared is a plus, so when I square minus x, I just get plus x squared. If I cube minus x, then I get minus x cubed. So I'm going to get a similar series, except every second term, all the odd terms are all going to be negative. And if I replace x with minus x in here, then I get 1 minus minus x is 1 plus x. And as I said, replacing x, if x is between minus 1 and 1, then minus x is also between minus 1 and 1. Now I can play with these two series. So I'm asked to find this series here. I can add the two series together, and everything will still work, everything will still converge. So when I add the series, I get 1 plus 1 is 2, minus x plus x cancels out, x squared plus x squared is 2x squared, the next terms will cancel, I'm going to get twice all the even number terms, and I just add the two things they converge to. It's 1 over 1 minus x on 1 plus 1 over 1 plus x. And I can divide, because the question actually said find 1 plus x squared plus x to the fourth plus forever. So I'm going to divide by 2, and I get this expression. And you could leave it like that, but I'm just going to, it does simplify nicely, so I thought I'd simplify it. So I put it over a common denominator. We multiply these together. Then we get 1 plus x plus 1 minus x. The x's cancel. So I just get a half into 2 over, and this is a difference of two squares here, so this is just 1 minus x squared. And then the 2's cancel, and I simply get 1 over 1 minus x squared. So that gives me a nice formula for the sum of 1 plus x squared plus x to the fourth and so on. It adds up to 1 over 1 minus x squared, and it converges provided I'm in the interval between x's between minus 1 and 1. Now, by the way, you may have realised, well, we could have also arrived at this by simply taking the original series here. We could have taken this series and just replaced x with x squared. I could have replaced each x here with x squared. And that would have given me 1 plus, replace this x with x squared squared is x to the fourth, and so on. And I could then just replace x with x squared here, and I would have gotten this one. So that's another way, in fact, it's probably an easier way in some ways, but I just wanted to show how you can add these infinite series together. We could also have subtracted the two. You might like to have a play with that and look at the difference between the two. If we take this series minus this series, we take this minus this one, and you can do a similar thing there. That's a nice exercise to do. Well, we can also multiply two series together, and that's a little bit more involved, but we'll just do a little bit of that, not too much. So I'm going to consider the two series 1 plus x squared on 2 factorial x cubed on 3 factorial. And if you think about it, this is that series we looked at a moment ago, which we proved was converges for all x. If you put this in sigma notation, it's just the series we had a minute ago, converging for all x. And we've got another series here, 1 minus x squared on 2 factorial plus x to the 4th on 4 factorial minus, and so on. Now you won't recognise this series just yet, but we will later. This is another well-known series. And you're given that both of these series converge everywhere. So you can put any x value you like into either series and they will converge. We want to write down the first three terms of their product. So we're going to multiply them together. Now that's a rather funny thing to do because these are infinite series. We're multiplying together two infinite series. We're going to get a new series, and I just want the first three non-zero terms in their product. So here they are. So I've got 1 plus x squared on 2 factorial, x cubed on 3 factorial, and so on. And there's the other series. Whoops, I should have had plus dot 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 in there, because they're two infinite series. Now how do we multiply them together? Well, you just do it systematically. You say, if you took a deep breath and took all the brackets out and expanded, then you're going to get this number, 1 times all of these numbers. Then you'll get plus x times all of these numbers, plus x squared on 2 factorial times all of these, and so on. Well, I like to do it systematically. So I say, well, if I did expand it all out, what will the constant term be? Well, the only way I'm going to get a constant is if I multiply 1 times 1. Everything else will have x's in it. So the constant term is just going to be 1. And now I say, well, what's the x term, the term with just one single x in it? Well, I get a one single x there. There's no single x's here. So I'm just going to get the x term by taking that x multiplied by that number there, 1. So the x term is just going to be x, a single x, from multiplying this one by that one. Now the x squared term's a little bit more complicated. I'll take a 1 from here, and I look along here till I find an x squared. There it is. So I'll get 1 multiplied by this term. That'll be minus x squared on 2 factorial. And the only other way I'm going to get an x squared term is if I take this one here from the first bracket and multiply it by 1 in the second bracket. So that's plus x squared on 2 factorial. And of course these are opposite in sign, so they cancel out, so that's not going to give me anything. How do I get an x cubed term? Well, I'm going to get an x cubed term. If I take a 1, there's no x cubed terms. If I take an x here and multiply it by an x squared term, then it'll give me an x cubed. So I'll get that term there multiplied by this term. And that will give me minus x cubed on 2 factorial. So that's that one here actually. So minus x cubed on 2 factorial I'll get from there. And I won't get anything from this multiplying into here, but I've got an x cubed on 3 factorial times 1. So if I multiply this one by this one, I'm going to get an x cubed on 3 factorial. So for the x cubed, I get x cubed on 3 factorial minus x cubed on 2 factorial. Now 3 factorial is 6, so this is x cubed on 6 minus x cubed on 2. And a sixth minus a half is minus a third, so I'm going to get minus a third x cubed. I leave you just to check that if you do 1 over 6 minus 1 over 2, you get minus a third, which is where this is coming from. Well, it only asks us for the first 3 terms, and I've now got 3 non-zero terms, so that will do. So if I were to take this and expand it all out, then the product will begin like this. The first 3 terms will be 1 plus x minus a third x cubed, and then plus dot dot dot. There'll be lots of other terms. We're only finding the first few. So that will suffice for this recording, and in the next one we're going to see we can also differentiate and integrate power series. Again, everything works very nicely, and we'll have a look at that in the next recording.